Hello and welcome to our Machine Learning Group assignment presentation for IT 4060 at SLIET. Our project is titled Predictive Analytics for Road Accident Severity Classification. We used a real-world dataset from the UK Department for Transport published on Kaggle containing tens of thousands of road accident records from Great Britain. Our goal is to predict whether a road accident results in slight, serious, or fatal injuries using 4 different machine learning algorithms. Each team member implemented one algorithm and will now present their findings individually. Thank you for your attention, and now let's begin our presentation. Hi, I am Tharindu Kavisha Pereira, and I implemented logistic regression for this project. Logistic regression is a linear classification algorithm that models the probability of each class using a softmax function. For our 3-class problem, slight, serious, and fatal, I used the multinomial variant. I chose this algorithm as our baseline model because it is fast, interpretable, and gives probability estimates for each class. For preprocessing, I applied standard scalar to normalize numeric features because logistic regression is sensitive to feature magnitudes. I handled the severe class imbalance, where slight accounts for 85% of records, using SMOTE to generate synthetic minority samples and setting class weight to balanced. The key parameters I used were solver set to LBFGS for multi-class support, max iterations set to 1000 to ensure convergence, and balanced class weighting. Looking at the results, logistic regression performed well on the majority slight class but showed lower recall on fatal accidents, which is the most safety-critical category. This is expected because road accident severity depends on complex non-linear relationships between features, which a linear model cannot fully capture. The most influential features were speed limit, lighting conditions, and road surface conditions. Overall, logistic regression provides a solid and interpretable baseline, but its linear nature limits performance on this complex dataset.
Hello, I am Lasiru Minruk Hewanayake, and I implemented the decision tree classifier. A decision tree partitions the feature space using a series of if-then-else rules. Each internal node tests a feature, each branch represents an outcome, and each leaf node assigns a class, slight, serious, or fatal. I chose decision tree because it is highly interpretable. We can visualize exactly how every prediction is made, which is very useful for understanding road accident patterns. For pre-processing, decision trees do not require feature scaling, so I skipped standard scalar. I applied SMOTE for class imbalance and set class weight to balanced. The key parameters I tuned were criterion set to Gini, max depth tuned via cross-validation to prevent overfitting, and minimum samples per leaf to control tree complexity. The decision tree improved over logistic regression in capturing nonlinear patterns. However, without careful pruning, it tends to overfit the training data. One major advantage is interpretability. The tree clearly shows that speed limit and lighting conditions are the first and most important splits, meaning these 2 factors are the strongest predictors of accident severity. The main weakness is overfitting. A single tree memorizes training data too closely, which reduces its ability to generalize to new accidents.
Hi, I'm Hansi Paboda Chandrasena. I implemented Random Forest, our strongest single-level model for road safety analysis. Random Forest is an ensemble method that builds hundreds of decision trees, each trained on random data samples and features, with final predictions made by majority voting. This ensemble approach dramatically reduces overfitting and produces a built-in feature importance score, making our predictions more reliable. For pre-processing, I used SMOTE for class imbalance and set balanced weighting to independently adjust each bootstrap sample. The key parameters were 100 estimators and random state 42 for reproducibility. This setup outperformed both logistic regression and standard decision trees. Analysis revealed the top predictors of accident severity: speed limit, lighting conditions, weather, road surface, and area type. These findings align with safety knowledge. High speeds in poor conditions are strongly associated with more severe accidents. Thanks for watching.
Hello, I'm Jayanga Pabasara. I implemented Cascade Random Forest, our most advanced model, also known as Deep Forest. Unlike standard models, it stacks multiple levels of classifiers to learn complex features. Probability outputs from one level are concatenated with original features for the next, similar to deep neural networks, but without backpropagation. I use SMOTE for class imbalance and a stratified 80-20 split to ensure data integrity.
This model achieved top performance, proving that hierarchical ensemble learning adds significant value to our problem. While training is slower, it significantly improved recall for the fatal class, the most critical safety challenge in our project. Now let's compare all 4 algorithms side by side. Logistic regression served as our linear baseline, fast and interpretable, but limited by nonlinear complexity. The decision tree captured nonlinear patterns better, though it was prone to overfitting. Random forest delivered the best balance of accuracy and generalization through ensemble averaging. Cascade Random Forest achieved the highest performance by stacking learning levels despite higher computation costs. In conclusion, ensemble tree-based models are most effective for classifying road accident severity. Key predictors include speed limit, lighting, weather, and road surface conditions. Identifying fatal accidents was the critical challenge, as they represent only 1 to 2% of the data. Thank you for watching. Our source code is on GitHub, and we're ready for the Viva.